Dear student, today we shall discuss another topic, that is photoelectric effect. This photoelectric effect also could not be explained by classical mechanics. This photoelectric effect also proves the particle characteristics of radiations. If the question comes, write one experiments which shows the particle characteristics of radiation. That is, one is photoelectric effect, another is Compton effect. So what is photoelectric effect? It is the, see, photo means light. Photo means light, and electric means electron. So there is, when light falls on a metal surface, electrons are ejected. That is, when light falls on a metal surface, there is emission of electron. This is called photoelectric effect. So definition is like this. It is the spontaneous emission of electron from the clean metal surface when a light of definite frequency falls upon it. I repeat the definition. It is the spontaneous emission of electron from a clean metal surface when a light of definite frequency falls upon it. Suppose this is our metal surface. This is our metal surface. This is metal surface. So when a light of definite frequency falls on it, instantaneously electrons are ejected from this metal atom. That is, it is the spontaneous emission of electron when a light of definite frequency falls upon a clean metal surface. So what is the definition now? Definition is, it is the spontaneous emission of electrons from a clean metal surface when a light of definite frequency falls upon it. So remember two important words here. Remember, this is the spontaneous process and definite frequency of the radiation. That is, process is spontaneous and there is a definite frequency of the incident radiation should be there. Now, some experimental observations of photoelectric experiment Now, what are the observations? Number one observation: for a given photosensitive surface, the incident radiation should have minimum frequency below which there is no emission of electron. That minimum frequency is called threshold frequency. That is threshold frequency. That is minimum frequency of the incident radiation below which there is no emission of photoelectrons. There is no emission of photoelectrons. These electrons are called photoelectrons. These are photoelectrons. So the threshold frequency is denoted by nu naught. This is the first observation. There should be a minimum frequency. Second observation. If the intensity of the incident radiation increases, I repeat, if the intensity of the incident radiation increases, the number of photoelectrons also increases. That is, number of photoelectrons is directly proportional to the intensity of the incident radiation. That is, when the intensity increases, number of photoelectrons also increases. Number third observation. If the frequency of the incident radiation increases, kinetic energy of the electrons also increases. I repeat, when the frequency of the incident radiation increases, kinetic energy of the photoelectrons also increases. That is, kinetic energy of the photoelectrons directly proportional to the frequency nu. So there is a relationship between frequency of the radiation and the kinetic energy of the radiations. Suppose this is the kinetic energy of the photoelectron and this is the frequency. Say frequency. Now you see, if the frequency lowers, there is zero frequency. No photoelectron will be there. So there should be a minimum frequency. So this is the minimum frequency. This is called nu naught, threshold frequency. From here, there is emission of electron, and electrons are there is a in this way kinetic energy increases with the increase of frequency. That is, kinetic energy increases linearly with the increase of frequency. Number fourth, see, each electron is bound with the metal surface. That is called potential energy. That is, there is a potential energy between the electron and the metal ion of the metal surface. This potential energy is called work function. That is this potential energy also called called work function W. That is the force between the electron and the metal atom, metal surface, is called work function. So that work function, that is that potential energy, should be overcome in order to eject electron from the metal surface. So this is that work function or that potential energy. Also we can say it is nothing but binding energy. So it is also binding energy. Secondly, that is when electrons ejected, there is ionization. There is ionization of the metal atom. So is also known as ionization energy or ionization potential. Ionization potential or ionization energy. So these are the some observations. Now we'll see next how these observations cannot explain by classical mechanics. I repeat, these experimental observations cannot explain by our classical mechanics. So next topic is failure of classical mechanics. Failure of classical mechanics. From the classical electromagnetic theory of light, we know energy is directly proportional to intensity. Energy is directly proportional to intensity. Now, if this is the correct, now if we increase the intensity of the light, if we increase the intensity of the incident radiation, then the kinetic energy of the photoelectron should increase. I repeat, if we increase the intensity of the incident radiation, then the kinetic energy of the photoelectron should increase. But what is our observation? If the intensity of the radiation increases, number of photoelectron increases with same kinetic energy. That is, intensity increases but kinetic energy does not increases. So classical electromagnetic theory here failed to explain these observations. Again, number one. Number two, okay, suppose kinetic energy of radiation is directly proportional to intensity. This is the classical electromagnetic theory of radiation. Now, if there is a continuous exposure of the metal surface by the radiation, which causes electron to gain more and more energy from the radiation, 1 hour or after 2 hours or 3 hours, even after 1 day, it will acquire sufficient energy from the radiation and ultimately it will able to eject from the metal surface. Since see here, there is a time interval here, there is a time interval, exposure and the ejection. Exposure of the radiation and the ejection of the electron, there is a time interval. But what is the definition of photoelectric effect? It is the instantaneous process. As soon as light falls, electrons are ejected. That is, again here proves that energy is not directly proportional to the intensity. So this is the failure of classical mechanics. Now, however, Einstein able to explain these experimental observations by taking the idea of Planck quantum hypothesis. So Einstein explanation. Einstein says that number one, when a radiation have a frequency nu, if a radiation having frequency nu consists of discrete photons and energy of each photons is given be equal to h nu. I repeat, Einstein take the idea from Planck's and he says that if the radiation has frequency nu, it has a discrete quanta and energy of each quanta is given by h nu. And each quanta, that is, these are also called photons. Second, suppose when this radiation strikes this metal atom, that is photon strike, now photon strikes this metal atom, the entire energy of the photon is absorbed by a single electron. So here probability of absorbing two or more photon is negligible. One photon, one electron. So what is the second idea of the Einstein? When a photon strikes the metal surface, the entire energy of the photon is absorbed by a single electron. Now, a part of that energy is utilized to overcome the force between electron and the metal atom, to overcome the force between electron and the metal ion, that is to overcome the work function, overcome the potential energy, overcome the binding energy. So a part of that energy is used to overcome the work function, and the remaining energy is utilized as a kinetic energy of the electron. So entire energy of the photon is divided into two parts. One part is to overcome the work function and the another part kinetic energy. So first is work function and another part is kinetic energy of the photoelectron. So we can also, h nu equal to work function is h nu naught plus half m v max square. So here see that nu naught, that is minimum frequency of the incident radiation to eject electrons. So there is the nu naught, and this nu naught, the incident nu naught, this nu naught should be the same. So this is called Einstein equation. Einstein photoelectric equation. Now, case 1, when nu is less than nu naught, that is incident frequency is less than threshold frequency, that is work function, no photo emission. The incident radiation is a lower frequency. case 2, when nu is equal to nu naught, there will be photo emission but zero kinetic energy. Photo emission with 0 Ke. And case number 3, when nu is greater than nu naught, electrons ejected with kinetic energy. Electron ejected with kinetic energy. So this is all about photoelectric effect. We will do some numerical problem on photoelectric effect. So this is the first numerical problem on photoelectric effect. Given, see, the question is the work function of sodium is 2.2 electron volt. Calculate the maximum kinetic energy of the photoelectron emitted when exposed to 200 nanometer of light. This first one. And the second one is largest wavelength that will cause photoelectric effect. So here, solution. See, given. So remember, when you solve this type of problem, try to solve in always in SI unit. So here work function is given. Work function is given, that is W equal to H nu naught equal to 2.2 electron volt. So 2.28 electron volt. So it should be converted into joule. 2.28 into 1.6 into 10 to the power minus 19 joule. We know 1 electron volt equal to 1.6 into 10 to the minus 19 joule. So it is almost equal to 3. You multiply it, you will get 3.648 into 10 to the power minus 19 joule. So we can solve this problem by using Einstein photoelectric equation. So what is Einstein photoelectric equation? We know H nu equal to W plus say Ke, or H nu naught plus half m V max square. Again, when I see here, work function we got, but light falls. When light falls, what is the wavelength of that light? 200 nanometer, not frequency given, it is a wavelength given. So here lambda, that is incident lambda, we can say lambda equal to 200 nanometer is given. So nanometer should mean meter, 10 to the power minus 9 meter. So in this equation we got nu value, that is from lambda value nu can be easily calculated. With the work function, kinetic energy can be easily calculated. So from Einstein equation, we have, or we know we have H nu equal to, so work function plus Directly kinetic energies as per question, kinetic energy. So we have to then kinetic energy is equal to h nu minus w. So what is h equal to c by lambda minus h nu already given. This is the h nu. Sorry, over w is given. That is w. Now put the values. Value of h is 6.626 into 10 to the power minus 34 joule second. The velocity applied 3 into 10 to the power 8 meter per second. What is the value of lambda? Just we have to calculate. Just now we have seen 200 into 10 to the power minus 9 meter minus, now w is value is this 3.648 into 10 to the power minus 19 joule. Now the student, you can calculate this one, but I have a calculation. So this value is 9.99 into 10 to the power minus 19 joule. So this is the maximum kinetic energy we have calculated. For second one, B, we got the kinetic energy. We have the work function. Just calculate for the second B number one, very easy. So h equals c by lambda equal to w plus ke. Ke value is this. Work function is this. C is known. H is also known. Lambda can be easily calculated. So I think you can do this. Our next topic is Compton effect. So this is another experiment which confirms the particle characteristics of radiation. So what is Compton effect? Compton observed that when a high energy beam, that is high energy photon like X-ray and gamma ray, that is high energy beam, X-ray gamma strikes a target, strike a surface, strike a charged body, atom, ions or crystals. When this high energy beam strikes, this beam gets scattered. It gets scattered. And he found that, he observed that wavelength of scattered photon is higher, longer than that of the incident photon. That is, lambda dash is greater than lambda. This observed change in radiation wavelength, or this observed change in radiation frequency of the scattering experiment is known as Compton effect. This change in wavelength, that is wavelength of the scattered photon is longer than that of the incident photon. This is called Compton effect. That is, lambda dash is greater than lambda, therefore lambda dash minus lambda equal to del lambda is called Compton shift. Compton shift. And this Compton shift is a function of angle of scattering. Now what is angle of scattering? Suppose this is the direction of our incident photon. So this is the angle of scattering, phi. He also observed that at the same time an electron also ejected from the crystals or from the charged bodies. That is called recoil electron. This is called recoil electron. That is called recoil electron. And this, say we denote at an angle of theta. So Compton observed that this Compton shift is a function of angle of scattering and is given by del lambda equal to h by m naught c 1 minus cos phi. What is m naught? Rest mass of the electron. Is the rest mass of the electron. Now, these experiments cannot be explained by our classical mechanics. This is also called failure of classical mechanics. So how the failure? Number one, according to classical mechanics, the wavelength of the scattered photon should be same of that of incident wavelength. That is, lambda dash and lambda should be same. But what you have observed here, that lambda is longer. And quantum explanation. This is Compton able to explain this phenomena with the help of Planck's idea, that is, or this phenomena by taking the particle characteristics of radiation. That is, there is a radiation consists of photons. So when a photon strikes an electron, there is an inelastic collision. I repeat, when a photon strikes an electron, there is an inelastic collision. Photon transfers energy and momentum to the electron. As a result, see here, photon transfers energy to the electron. Definitely, scattered photon should have lower energy because energy transferred, na? That's why scattered photon have lower energy. Lower energy means longer wavelength. And the recoil electron gain energy from the photon. And this is only possible particle characteristics of radiation. Next is derivation of Compton shift. Derivation of Compton shift. That is del lambda equal to h by m naught c 1 minus cos phi. We have to derive this Compton shift. So to derive, we have to write some things. So what is the energy, initial energy of the photon? Energy of the photon, say EI equal to h nu. Suppose nu is the frequency. So energy of the photon is h nu. And what is the momentum of initial momentum? That is h nu by c. Means why we are writing? Because we can derive this Compton shift by applying both law of conservation of energy and law of conservation of momentum. Now what is the energy of scattered photon? Say it is ES. So it is ES is equal to, say, h nu prime, or if energy momentum of scattered photon is equal to h nu prime by upon c. Now, what is the energy of the recoil electron? That is relativistic energy. That relativistic energy can be related to the momentum, and it is given by, that is, energy of the recoil electron say energy of the recoil electron, say energy is the equal energy small e for electron is equal to, we can write, say p square c square m naught square c to the power 4 to the power half. And what is the momentum? Say it is written as, say, momentum of the electron is, say it is pe. Momentum of the recoil electron is written as pe. Now first unlock applying law of conservation of energy. What is the initial energy? Initial, that is total, say total final energy is equal to total initial energy. So we can write, say total final energy is equal to total initial energy. So what is the total initial energy? Energy of photon, that is h nu plus energy of the electron is given minus 10 m naught c square. And what is the final energy? Final energy due to photon, that is h nu prime plus energy of the recoil electron, that is pe square c square plus m naught square c to the power 4 half. Energy of the scattered photon, energy of the recoil electron, incident energy of the incident photon, energy of the electron when it is at rest. Now we do mathematics here, simple mathematics to simplify. So here pe square c square plus m naught square c to the power 4 half is equal to, transfer this side, h nu minus nu dash plus m naught c square. Now by squaring both sides, remember this is a, this is b, a plus b whole square. Now when squaring it becomes p square c square plus m naught square c to the power 4 equal to h square nu minus nu dash all square a square plus m naught c to the power 4 plus twice h nu by nu prime into m naught c square, a square plus b square twice a b. Necessarily this quantity cancel out. So finally finally dividing by c square. Now dividing by c square, we get say this is, I'm writing here PE square equal to AC square by C square nu prime square plus, here C square is cancel out, twice H nu prime m naught. So dividing by C square, this is cancel out, this is by C square, this will cancel out, okay, this is equation number 1. So this is due to energy. Now applying law of conservation of momentum. So applying law of conservation of momentum, so it is number 2. We get, so I'm right, law of conservation of momentum. So here, see, energy is scalar quantity, but momentum is a vector quantity. So momentum is a vector quantity. So now it has, so in this momentum is there, that this momentum can be resolved into two components. For example, suppose this is our momentum of scattered photon, PS. So this point can be resolved in this x direction. So this is our x direction and this is our y axis, the y direction. So this is our y direction. So this is our angle of scattering. So this is same. So what is the value? What is the value of this? This is of course PS cos phi. And what is the value of this? This is PS sin phi. Similarly, momentum P, momentum of the recoil electron, that can be resolved into x and y. So for electron will be direction like this. Say this is our PE. So this is x direction, this is y minus y direction, this is minus y. So this is our theta. So what is the force? This force is PE cos theta, and this is minus, so this is can be written as minus PE sin theta. So this is, so I'm writing here, this is PS sin phi and this is PE sin theta in this direction. So one due to PS cos phi and another due to PE cos theta. Now number A for the x-axis. For the x-axis. So for the x-axis, what is the initial momentum and what is the final momentum? Initial momentum is, this is, say, Pi due to incident photon plus 0 due to electron, and x direction momentum due to PS cos phi plus PE cos theta. This is x directions. So in the y direction, y axis, our photon moving in the x direction. So initially no scattered, so there is no contribution in y one direction initially before scattering. So before scattering, initial momentum is 0 due to photon plus 0 due to electron. Now equal to in y direction, due to scattered photon is ps sine phi minus pe sine theta. Now we do some mathematics, or pe cos theta is equal to pe cos theta is equal to pi minus ps cos phi. Now squaring both sides. Pe square cos square theta minus pi square plus a minus b whole square, ps square cos square phi minus twice pi ps cos phi. In this side, say pe sine theta is equal to ps sine phi, squaring both sides. Pe square sine square theta equal to ps square sine square phi. So this is equation number 2. This is equation number 3. Now adding equation 2 and 3. So here this is C. P square, left side p square common. So let us write p square cos square theta plus sin square theta. Left side is okay. That right side pi square, again ps common, ps square common, cos square phi plus sin square phi minus twice pi ps cos phi. After simplification, we will get that here from 2 and 3, equation 2 and 3. There is pe square is equal to pi square plus ps square, this is equal to 1, this is equal to 1, this is equal to 1, minus twice pi ps cos phi. So equation number 4. So we got the equation number 4. See the equation 1 and 4, left side equal, so right side equal. So from equation 1 and 4 we can write this equal to this. Now from equation 1 and 4 we get h square c square nu minus nu prime whole square plus twice h nu minus nu prime m naught, this portion we have written, okay, equal to this portion pi whole square plus ps whole square minus twice pi ps cos phi. Pi square ps square, I think. Okay, so we can erase this. Now we can put the values pi ps from these equations. So here again a minus b whole square, a minus b whole square, so we get directly, we can write ac square c square, so it is a new square, so one is a new square, plus a square plus b square, again h square c square, new prime whole square, plus minus h square c square into twice new prime, plus twice h new minus new prime m naught equal to, this is pi, new by new h, new upon c, h square new square upon c square, plus ps h square new prime square c square minus twice p pi h new upon c into h new prime by c cos phi. Now see, this quantity cancel, this quantity cancel, so we'll get these two cancel, these two cancel, again here see, oh, we can take some common. Okay, so let us write one more steps, then it will be okay. Finally, that is, we can write minus h square c square twice new prime plus twice h new minus new prime m naught is equal to, here minus twice h square c square new prime new prime cos phi. Now this quantity, if you take this c here, h square 2 common, h square c square is common, new prime common, so on the left side if you keep it twice h new minus new prime m naught equal to the right side, that's the common is minus 2 h square c square new prime common, will get 2 common is common, 1 minus cos phi. Or here again 2 to cancel now, 2 to cancel now. Now new converted into lambda will get, even then one h cancel out, see one cancel out, so it is say c by lambda minus c by lambda dash m naught is equal to h by c square into c by lambda into c by lambda prime 1 minus cos phi. See here, c square cancel out. Now if we take a LCM here, lambda prime, say c, it is lambda prime minus lambda m naught equal to, we can write c is cancel out, say h by, not c is there now, lambda prime, say 1 minus cos phi. Now you see, this cancel out. Finally we will get c. Now finally lambda dash minus lambda prime minus lambda is equal to h by, there is m naught, c come lower, these two cancel out, and this side 1 minus cos phi. So which is the Compton shift? So we have successfully derived Compton shift. So thank you for watching this video.